So let's look at the generators of SUN. The explicit generators. And this is a choice that is consistent with the properties that we derived. There are other choices as well, okay? So it doesn't have to be exactly it. So this is the choice that I came up with, say. So they, the generators of SUN, consist of the following types. Okay, so number one is the diagonal matrices, Hermitian traceless diagonal matrices. So for example, H1. So these are n by n matrices. So this is 1, 0, 0, dot, dot, dot. These are sparse matrices, so everything else that I'm not specifying is 0. So this is H1. Of course, it's Hermitian and it's traceless. H2 is 0, is the one where 1 is in the 2-2 element, okay? And if we are dealing with SUN, it's clear that we can only go up to Hn-1 for this type of matrices. Right? That's clear, right? So, so we have generated a set of n-1 mutually commuting generators as well. That's an important observation. And we'll see that this actually forms the Cartan subalgebra. That these matrices form the Cartan subalgebra of SUN. So what are the other types of matrices? So this is type A. Type B is n-1 by 2 real symmetric traceless matrices. Okay, matrices. And the way we do this is we label them with A greater than B. Otherwise, the counting is not going to be right. So TAB, so A is always greater than B. And so A and B can take values from 1 to n, but A has to be greater than B, so we don't overcount. So the CD element of this matrix is half delta A delta B CD plus delta A delta B DC. It should be clear that this is a symmetric matrix, right? And also that it is traceless. Okay? And because A is greater than B, the number of elements, the number of matrices is n times n-1 by 2. Is this clear how the counting works, or I can show it as well? How would you count this? How would you come up with this number? Can someone tell me? From this condition. So let me show you how we do this. So suppose that A and B themselves, so these are labels, right? But the labels we can form a matrix out of them in principle. So these are the labels. Say A goes this way, B goes this way. So this will be an n by n matrix, right? So for an n by n matrix, how many elements are there in the diagonal? There are n elements, right? But in total, there are n squared elements. But we are only interested in these, counting this number, right? Where A is A greater than B or B greater than A? It doesn't matter. One is greater than the other, right? So what do? We say, okay, you know, the matrix has n squared elements, and we subtract from it the number on the diagonal. So and then we just divide it by 2. And if I simplify it, it's n minus 1 by 2. And this is the number of real symmetric matrices we have. Okay, so that is how this condition leads to this number of matrices. Okay, and we know that it has to be because it's real, if it's going to be real and Hermitian, it better be symmetric, right? Otherwise, it won't be Hermitian. It'll be, so it has to be symmetric. So up to normalization, you know, this is what we have. You know, we know that we can write this. And because A is never going to be equal to B, so, you know, this will basically give us, A is always greater than B, it'll gonna give us, when we take the trace, it's going to give us 0, okay? So, and do you know how to take a trace of a matrix? If we have a matrix AB and its element is CD, then the trace of this matrix is we contract the Kronecker delta with the matrix, okay? So if I now go back to my original expression, it's delta A, delta B, and here we have C of D plus delta A, delta B, here we have D and C. And then we are tracing it with C and D, because this is the identity, you know, yeah. Okay, this is basically trace of T of AB is, because this means that this is equal to T of AB CC, right? So that is what we call by trace. And now if you do this, you know, because of this guy, wherever you have C, it becomes replaced by a D. So we have half delta AD, and delta BD plus delta AD delta BD. And then we do another sum so that whenever in the first one, I think, yeah, everything is fine. So in the first, so we can replace D by B. So we have A, B times 2. And because A is greater than B, this is never equal, A is never equal to B, that means it's going to be 0. Yeah, so I made a mistake somewhere because, no, it's fine, yeah. Maybe I should just, yeah. Okay, so any questions? Okay, I'm not sure if those are questions of silence of confusion or silence of understanding. So we also have another set. We haven't exhausted all the possibilities of Hermitian traceless matrices, because we can have imaginary and antisymmetric matrices. And by the same counting argument, we have n minus 1, similar counting by 2, antisymmetric, pure imaginary matrices. Okay, so these matrices, let's call them T tilde AB. We are not Am I putting any condition on the? No, I'm not putting any condition on the indices because I think what is happening is, yeah. Yeah, we can impose that as a condition. So then this matrices can be, we just multiply by I, and then instead of plus sign, we have minus sign. Okay, so this is, and because it's antisymmetric, the antisymmetry is in CD, right? As well as these guys. Because it's antisymmetric, anything that is antisymmetric is automatically traceless. So the total number, let's check that the dimension is fine. We have n minus 1 in the Cartan subalgebra plus n times n minus 1 by 2 plus n times n minus 1 by 2. And if I add everything up, I have 2n minus 2 plus n squared minus n plus n squared minus n. So we have 2n and minus n minus n. And then we have n squared is 2n squared minus 1 by 2, n squared minus 1. So the dimension, say, of SU2 according to this formula is 3. So that means it matches our expectation. Okay. I'm a little unclear about, well, we can do two things. We can impose that A is greater than B, or we can say this. So I think the two things are the same. But what's important is that it's antisymmetric in its indices. Okay, any questions?
Sir, why was different notations, like what did the different notations H and T mean? I was a bit confused.
Oh, yeah, the T's are essentially the H's are, I'm using H for the Cartan subalgebra, the maximally commuting set. And if you draw this matrix, you can show that these matrices don't commute, that the elements of H, they all commute, right? Because they're all diagonal matrices. But they won't commute, none of them will commute with any of these guys. So the T's are the non-Cartan subalgebra elements, and the H's are the Cartan subalgebra elements. Okay, Nahi?
Oh, okay, sir.
Okay, let's take a 15-minute break and then meet back here at 8:45, okay? Okay, so let's start again. Now, I want to take a step back and talk about something that I kind of glossed over. I was just thinking about it. Is this thing that why are we choosing A greater than B? And I also said, well, we can just take AB to be negative, to be antisymmetric. So the idea is that if we have a group, let me just make it a bit bigger. If we have a Lie group, of say n dimensions, what does it mean? It means that it means we have n linearly independent generators, right? So that's why the counting is important, you know, because SUN has dimension n squared minus 1. So the dimension of, and we know that the generators of SUN need to be Hermitian and traceless. So, so we can either choose A to be greater than B for the antisymmetric imaginary generators, and or, you know, if A is not greater than B, then we have to impose this condition. Because then you can see that this guy is not linearly independent of TAB. So it gives me exactly the same number of generators. And because of this antisymmetry T00 or T11, well, the TAA in general, T tilde, because I'm using T tilde here, T tilde AA, these are zeros. Okay, so that's just a one minor point I wanted to clear up. Any questions?